This problem focuses on understanding how the gaussianprocessor in SCIKITLEARN works with a specific type of kernel called the PairwiseKernel. I'll be analyzing the properties of the resulting kernel matrix. I'm given a gaussianprocessor using a PairwiseKernel with a linear metric and a gamma value of 0.5. I need to determine which statements about the resulting kernel matrix are true. This statement asks whether the kernel matrix K is symmetric. A symmetric matrix is one where the value at position I, j, is the same as the value at position j, I. This statement claims that the diagonal elements of I, I, represent the squared Euclidean distance of each data point from the origin. I'll need to investigate if that's true given the linear metric and gamma value. This option checks my understanding of how the kernel matrix element K, I, j, is calculated using the dot product of data points I and j, scaled by the gamma parameter, gamma. This statement tests my knowledge of a fundamental property of kernel matrices. A positive semi-definite matrix ensures the validity of the gaussianprocess. This refers to the overall properties of the kernel matrix generated by the PairwiseKernel, such as symmetry and positive semi-definiteness. These are key characteristics that I need to understand to answer the questions correctly. I'm using scikit-learn's gaussianprocessor with a PairwiseKernel to model data. Think of it like building a sophisticated prediction machine using a special type of math. This is the core of my prediction machine. The PairwiseKernel uses a linear method to compare data points. It's like comparing how similar two things are by looking at their linear relationship. The GAMMA value, 0.5 here, just adjusts the strength of this comparison. It's a scaling factor. This is the result of the pairwise comparison of all my data points. It's a square matrix, nxn, where n is the number of data points. Each element k, I, j, tells me how similar data point I and data point j are. According to the PairwiseKernel, my data is made up of n data points, each with d features. Imagine each data point as a point in a high-dimensional space, like a point in 3D space, but with possibly more dimensions. I'm using scikit-learn's PairwiseKernel to create a kernel matrix. The setting tells the function to use the dot product for calculating pairwise similarities between data points. The parameter scales down this dot product by half. My data points live in a space with d dimensions, meaning each data point is described by d features or attributes. For example, if I'm looking at images, d could represent the number of pixels. The PairwiseKernel function generates this matrix, which shows how similar every pair of data points is. Each entry represents the scaled dot product of the ith and jth data points. I have a total of n data points in my dataset. Each of these is a point in the d-dimensional feature space described above. This is a multiple-choice question evaluating my understanding of how a PairwiseKernel with a linear metric functions and the properties of the resulting kernel matrix. Specifically, I need to determine which statements accurately describe the resulting kernel matrix. I'm using a Gaussian process regression model to understand relationships within my data. The core of this model relies on a kernel function to express how similar data points are, and PairwiseKernel provides that function using the linear metric and gamma value described earlier. I'm using a Gaussian process regressor, a powerful machine learning model, to predict values. I'm using a special type of kernel called a pairwise kernel, which calculates relationships between data points in a specific way. Let's imagine you have a bunch of data points. Each point has multiple features. Think of it like describing a person based on their height, weight, and age. N is just the total number of data points, and D represents the number of features for each point. The pairwise kernel is what makes the magic happen. I'm setting the metric to linear, meaning I want it to calculate the relationship between data points using the simple dot product. The gamma parameter acts like a scaling factor. I set it to 0.5, meaning the results will be half of what the dot product would be on its own. The result of the pairwise kernel is a kernel matrix, which is an nxn matrix, n rows and n columns, where n is the number of data points. Each element k, I, j, in this matrix represents the relationship between data point I and data point j is calculated by the pairwise kernel. This matrix holds vital information about the relationships between data points that I will later use in the regression. The diagonal elements, k, I, of the kernel matrix are not the squared Euclidean distances from the origin. They are actually the dot product of each data point with itself, scaled by gamma. It would be the squared Euclidean distance only if my data is centered at the origin. For any two data points, I and j, the element k, I, j, in the kernel matrix represents the dot product of those two data points, scaled down by a factor of gamma, 0.5 in my case. This dot product essentially measures the similarity between the two data points. A crucial property of kernel matrices is that they are positive semi-definite. This is a mathematical requirement. It guarantees that the resulting Gaussian process is valid and behaves as expected. It ensures that certain calculations, essential for the model, will always give meaningful results. Think of it as a necessary condition for everything to work smoothly. Because the dot product is commutative, the order doesn't matter. AB equals BA, the kernel matrix K will be symmetric. This means K, I, J, will always equal K, J, I. Neat, huh? I love this one. A positive semi-definite matrix is a fundamental property of kernel matrices. It's like a guarantee that the Gaussian process model built using this kernel will behave nicely. It ensures the model's validity. Think of it as a necessary condition for a well-behaved Gaussian process. Okay, let's break this down. K, I, J, represents a single element in our kernel matrix. The subscript I and j refer to two different data points. The value of k, I, j, is calculated by taking the dot product, a way of multiplying vectors, of data point I and data point j, then I multiply that result by gamma, which is a scaling factor, 0.5 in your example. It's a simple scaling of the similarity between those two data points. I see this is often misunderstood. The diagonal elements of the kernel matrix, k, I, actually represent gamma, times the dot product of data point I with itself. This is not directly equivalent to the squared Euclidean distance from the origin unless the data has been pre-processed, centered and normalized. The squared Euclidean distance involves a calculation of the difference of the coordinates and their squares. It is not what you directly obtain here. I'm focusing on a dataset with n data points, each having d features. Think of it like n different people, each described by d characteristics. For example, n could be the number of houses and d could be the number of features for each house, size, price, location, etc. I'm using a specific tool called a PairwiseKernel from Sklearn, a popular machine learning library. The linear metric tells it to calculate the similarity between data points using their dot product, which is kind of like measuring how much they point in the same direction. The gamma value, 0.5, scales this similarity score down by half. The PairwiseKernel creates a square table, nxn, called a kernel matrix. Each cell k, I, j, tells us how similar data points I and j are. It's like a similarity map for all the pairs of data points in my dataset. I'm evaluating the properties of this kernel matrix. Is it symmetric? What do the diagonal values mean? What does each cell in the matrix represent? Is the matrix positive semi-definite? These are the crucial questions I'm addressing here. I'm checking if the kernel matrix K is symmetric. A symmetric matrix is like a mirror image along its diagonal. The value at k, I, j, will always be the same as the value at k, j, I. Here, I'm looking at how the kernel matrix represents the relationship between two specific data points. Specifically, k, I, j, is calculated as 0.5 times the dot product of data point I and data point j. I'm verifying if the kernel matrix produced always satisfies the positive semi-definite property. It's a crucial mathematical characteristic for a valid kernel matrix.